This is a bridge made entirely out of paper. It can support one person's weight on its 950mm span.
Okay, I'm standing on the bridge. Hands are off. Yep, it's pretty stable actually.
And here is our journey to build and test the bridge. The challenge is simple. We need to build a bridge over a valley that is 950mm wide and 600mm deep, with a piece of 32-inch by 40-inch matboard and a bit of glue. The bridge needs to carry 1,000 newtons of force, which is equivalent to about 100 kilograms. More force it can carry is obviously better. Before actually constructing the bridge, we first need to figure out what makes the bridge stronger. Well, if we have a piece of paper, one is placed across 2 points, it's just gonna bend. So one way we can make it stronger is by making the bridge thicker. And when the bridge is thicker, we can apply much more force on the bridge without actually failing it. But now another issue occurred. When we apply too much force, well, it just breaks. The bridge could break due to a lot of reasons, such as having too much tension, too much compression, having too much shear across its page, and it could buckle when it's really long and thin. All of which should be accounted to determine the ultimate strength of the bridge. At this point of time, it is also important to understand the structural properties of the matboard, such as how much force I can put on the piece of matboard before it breaks into 2 pieces. And that involves a lot of distractions. Never mind. I'll set up some equipment to do this. Okay, so now we understand the material better. Let's start designing the bridge and actually build it. So here's the plan. I have 20 milk jugs, weighing 4 kilograms each. And I also have 4 car tires, weighing around 20 kilograms each. This is our first concept. It did not utilize the bottom of the valley. In theory, it should withstand 2,500 newtons of force, which translates to 250 kilograms of weight. So this bridge should be able to handle all the weights I have prepared for it. 16 kilograms, 32 kilograms. Well, technically the bridge didn't break. It fell because it's rather tall and thin. When we're doing the calculations, we assume the load is pushing directly downwards. which is a big design oversight because in reality, the load is never pushing straight down. There's always some sideways forces. Let's try again then. Second tire. Okay, it's embarrassing to say. The bridge is predicted to fail at 250 kilograms, but in reality, it failed at 104 kilograms. It failed at less than half of the predicted load. But with some closer inspections, instead of any calculation errors, I think the failure is more likely to be caused by me improperly gluing the piece together. Well, you see, contact cement only work if they are in contact, and these central diaphragms are nowhere near the top flange. Anyways, let's move on to concept 2. The second concept should be able to withstand 270 kilograms. So hopefully it can perform better than this first bridge. All 4 tires added. At this point, it's not a matter of whether this bridge can take all the weights. It's a question of whether I can line them up perfectly so that they don't collapse on themselves. It probably means the bridge is, well, okay. Well, it's getting a little awkward. The second concept broke at only 60% of its set capacity. If I may demonstrate my theory using this piece of leftover matboard, imagine this is a cross-section of a bridge deck. My speculation is that the weights were leaning towards the far side of the bridge, causing it to deform more than the front panel, and the extra deformation at the back caused the weights on top to lean backwards even more. This created a positive feedback loop that magnified the issue and caused this final failure. But with some close inspections, I think the only structural thing that broke is this joint between the support and the bridge. The part designed to withstand compression gets separated during the collapse. With that being said, I bet I can still stand on this bridge. Hello, future me here. In this clip, you might not be able to see the top half of my body, but I assure you I'm standing on the bridge without any assistance. Okay. Okay, so we made a bridge out of matboard paper. Well, 2 in fact. And the second concept can support more than double of my weight. Although the bridge wasn't performing as well as the prediction, I think we learned some valuable lessons, such as how assumptions play a big role in calculations, and the importance of factor of safety. Well, anyways, I think it is enough rambling from me. Thank you so much for watching.